Hello. So, the last lectures that we've discussed have all been on single degree of freedom structure. Whether they were real structures, for example, the one-story, one-bay frame that we looked at was a single degree of freedom with rigid beam, of course. And then we looked at generalized single degree of freedom, where if it was a rigid body assemblage, it was a true single degree of freedom system. And if it was a flexible, we saw that by considering only one unknown and defining shape functions, we could define that as generalized single degree of freedom systems. From today, what I am going to be starting off is by looking at systems which cannot be classified as single degree of freedom systems, and therefore, these are what are known as multi-degree of freedom systems. So, what I am going to be looking at from today onwards for the next few lectures is going to be, and today especially we are going to be looking at equations of motion for multi-degree of freedom structures. Okay. So, let us start looking at one of those, because as you see that what is a multi-degree of freedom. Let us first define that before we start looking at equations of equilibrium, etc. Okay. And so, let us look at what a multi-degree of freedom system looks like. Well, let me take this problem. So, what we have is a rigid bar which cannot move in this direction, it is restrained. Okay. So, this is a rigid bar. Okay. And what I am going to do is, this one only ensures that this one does not move in this direction. The basic things that we are looking at are here. And let me take a situation where I have so, this is a rigid beam on elastic foundation. Okay. So, this is a rigid beam on elastic foundation, and let us say that the subgrade modulus is given as K Newton per meter per meter. Okay. So, that is like the subgrade modulus. So, this is like a spring constant per meter. So, this is the spring constant in a per meter sense. We also look at this having m bar, which is mass per unit length. So, this is the stiffness per unit length, and this is the mass per unit length. Okay. This is a classical rigid beam on elastic foundation problem, and let us just assume that the length of this bar is L. Okay. So, now let us see how this problem needs to be solved. Okay. So, having defined the problem, I am going to again now look at this bar, and now the only thing is that since we know that this bar is not going to move in this direction, I am not putting that thing. I am just saying it is restrained from moving in this direction. It is only allowed to move in this direction. if you look at this bar, okay, now it cannot move in this direction. Okay. So, it can only move in this plane. Now, if you look at this, okay, what are the possible degrees of freedom of this? Now, it is obvious that this motion is a degree of freedom. What else? Well, actually we look at it, this bar can rotate also, right. I mean, if you look at it, it could move like this. Okay. It could move like this. So, if it moves like this, then what happens? Essentially, that essentially means that this beam has 2 degrees of freedom. Note that this motion is not allowed. Remember that this is not allowed. Okay. So, if we look at it, I can define this structure as a 2 degree of freedom structure by saying that, look, I am going to take, see, this is a beam, okay, rigid beam with uniformly distributed mass. The mass m bar is a constant. So, there the center of mass of this bar will be where? It will be the center, which is L by 2. So, let me take the center of mass of the bar and let me say that this is the center of mass. So, I am going to define 2 degrees of freedom at the center of mass, u x and u theta. Okay. So, now how is this different from the problem that we had looked at last time? If we looked at last time, we had seen that the bar was like this. Remember the previous problem that we looked at, rigid bar, right. So, it could only rotate about this point. Now, since this is allowed to move up and down, it can not only rotate, it can also move up and down. So, therefore, there are 2 degrees of freedom for this structure. Okay. So, if you have 2 degrees of freedom, so I have k star and m star, and I have defined my degrees of freedom at the center of mass. Now, there are various ways. As far as we know that there are 2 unknown displacement quantities that can define the motion of this bar, we call it a 2 degree of freedom . 2 degree of freedom structure. Okay. So, now once we have this 2 degree of freedom, what happens? Well, let us see how we can solve this particular problem. Okay. If you look at this, what you have over here is, well, let us look at it. So, now I am going to just do this as a line. Okay. So, I have u x and u theta defined at the center of mass. Why is this? Why is the geometric center the center of mass? Well, the mass is uniformly distributed. So, obviously, the center of mass is the geometric center. So, these are my 2 degrees of freedom. So, now if this is 2 degrees of freedom, what do I do? Well, I look at what displacement do I get for each degree of freedom. For u x, if u x is equal to 1 and u theta equals 0, then what do we have? Since there is no rotation, it just means that you have a u x rigid body displacement at every point. This is u x. So, that is u x equal to 1 and u theta equal to 0. Let us look at the second degree of freedom. What happens when we put the second degree of freedom in? Well, what we get is the following: u theta equal to 1, u x equal to 0. That means the center cannot go up and down, it can only rotate. So, when it rotates, remember small displacements, right. So, this, if u theta is equal to 1, this is L by 2 and this is L by 2 here. So, that becomes my 2. So, if I look at this, this is equal to 1, this is equal to 1, and therefore, if I look at xi 1 x, xi 1 x is equal to 1. Okay? And what is xi 2 x? This shape is xi 2 x. So, if you look at xi 2 x, well, I do not need to go through the what xi 2 x is, but if I take x from here, then xi 2 is equal to 2 x by L. Sorry, it is u theta equal to 1. So, it will be x upon L, sorry, in x into L into L. So, this is xi 2 x is equal to x. Okay. So, these are my this. So, now let us look at this. Now, let us look at a situation. So, how do I solve this problem? Well, remember how I solved this problem. Earlier, what did we say? Well, given this displacement, right? Given this displacement, I find out the forces acting on the structure. So, given this displacement, what are the forces acting on the structure? Well, I have one which is the F I, which in this particular case is equal to m bar dx. Okay, F I is inertial force per unit length, and that is equal to m bar dx, that is equal to this into xi 1 into what? U x double dot. That is my F I. Similarly, I have my F s, and that is equal to k bar dx into xi 1 into u x. Okay. So, those are the forces here. And what are the forces due to this displacement? Well, similarly, F I is equal to m bar dx into xi 2 into u theta double dot, and F s is equal to k bar dx into xi 2 into u theta. So, this is the forces in this particular one, and these are the forces in that one. So, now what I want to do is, I want to find out, now understand that, remember this, that how will this equation look like? This equation, I mean, let me first write down what an equation looks like, and the equation looks like this: the vector of F i's plus the vector of S's is equal to the vector of loads. Okay. That is what we have. F I plus F s is equal to F. Okay. And if I really look at this, okay, and what are the degrees of freedom? The degrees of freedom in this particular case, u is equal to u x and u theta. Okay. So, now if u is equal to u x u theta, okay, what is F I equal to? By taking an analogy, F I is equal to, look at these units. this is going to be equal to 2 by 1. This is going to be 2 by 1 for this 2 degree of freedom. This is going to be a 2 by 1. This is a 2 by 1. So, this is a 2 by 1 and here I have the u, okay, which is a 2 by 1. So, relate the inertial forces to the acceleration vector. This is going to be the mass and that is going to be a 2 by 2. Similarly, for F s is going to be equal to k into u, where k, if since this is also a 2 by 1, this is a 2 by 1, this is a 2 by 2. Okay. So, essentially remember in the generalized single degree of freedom, we had to find out m star, k star and p star. Here what we are doing is we have to find out M matrix, the K matrix and the P matrix, I am sorry, P vector. P vector is the load vector. Okay. And so, these are the things that you have to find out in this particular case. So, if you really look at it, how will this equation look? Now, this is what we need to find out. Okay. And note that these are not property matrices. These are, this is mass matrix. This is stiffness matrix. This is load vector. Okay. And none of all of these correspond to u vector. I will explain this to you corresponding to this particular problem that we are solving over here. So, look back at this, and that is that if you really look at this particular problem, I have f s, f i, here I have f i 1, f s 1 and this is f i 2, f s 2. This f i 1 is due to, if you look at this f i 1, this is due to the u x displacement. Okay. And your f s 1 is also due to the u x displacement. Okay. And f i 2 and f s 2 are due to the u theta displacement. So, if you really look at this, this is going to be equal to u l. Okay. Okay. So, having done that, now how do I solve this particular problem? So, therefore, if you really look at it, if I give it any arbitrary displacement, okay, if I give it any arbitrary displacement, what is f I equal to? F I is going to be equal to a sum of the both. So, f I is going to be equal to, I mean this is not f I, this is the mass per unit, I mean inertial force per unit length, that is going to be equal to m bar dx y 1 u x dot plus m bar dx into xi 2 u 2 theta. So, this is the mass, this is the inertial force on bar. Okay. Similarly, so this is not your, this is like the inertial force on the bar. Similarly, the the resistance force is going to be equal to k bar dx xi 1 u x plus k bar dx xi 2 u theta. Okay. So, that is my F s. Okay. So, these are the over an infinitesimal element, these are the forces, the inertial force and the spring force over an infinitesimal length. Okay. So, now what we are trying to find out? We are trying to find out, and let us put some load on it, otherwise what do we do? So, let me put some load on it, and I will say that look, I am going to put I am going to put a triangular load, okay, where this is going to be P bar 0. So, this is the intensity at this point, and of course, at this point it is 0. Okay. So, it is a triangular loading, and if you have a triangular loading, okay, so therefore, we also have that load on that, and on top of that we have load which is given by how? It is given by let us look at it. So, it is going to be P bar if x is defined from the center, right, x is defined from the center. So, load will be, well, let me not belabor the point, the load will be in this fashion, 0 over the length L and P naught at the end. Okay. So, these are all the loads that you have on the structure. So, now what are we trying to find out? Remember that we are trying to find out, if you look at this, the old one that I had given, if you look at it, these that you have are actually corresponding to the degrees of freedom u. So, these are the inertial force, the equivalent inertial force corresponding to. So, from all these forces, I have to find out the equivalent inertial force, the equivalent spring force and the equivalent this thing defined at which point? Well, corresponding to the degrees of freedom means I want to find out, what I want to find out is this. I want to find out that given this bar, given all these loads, right, I have the inertial forces, okay, I have the spring forces, I have the load. I want to find out what is Fi 1, Fi 2 and similarly Fs 1, Fs 2 and the load F. Okay. I want to find out F1, F2. So, these are what I want to find out corresponding to. So, these are the force directions are given in this fashion. So, now if I want to find out the equivalent force, suppose I want to find out F1, how do I find out Fi1? Well, remember that to find out a force, a real force, and using the principle of virtual displacement, what do I do? Corresponding to the degree of to that force, I give a virtual displacement. What is the virtual displacement? If I give this, what is the virtual displacement? The virtual displacement is equal to, at any point, the virtual displacement is given by delta V is equal to xi 1 delta u x, if you look at it, right, delta u x. So, therefore, what happens is, if I want to find out F I 1, Okay, that is the inertial force only. So, I have to only take the inertial forces. F I 1 becomes the following. F I 1 becomes F I 1 into delta U x. That is the work done by the equivalent inertial force, and this has to be equal to, well, let me look at the F I. Now, F I, which is the mass, the inertial force per unit length, okay, into xi 1 delta U x, and integrated over the whole length. Okay. So, this is what this is equal to. So, therefore, delta x exists on both sides. So, F I 1 is equal to, and let me substitute F I. What was F I 1? It was equal to m bar dx xi 1 into u double dot x plus m bar dx xi 2 u double. So, this is my F 1 all into xi 1 into, well, that is all xi 1, because del u x and del u x have been, and this entire thing is to be integrated from 0 to L. So, if I now put this together, what does this become? If you look at F I 1, this becomes the following. If you look at this, this becomes m bar I can take outside, and u, these also I can take out. So, this becomes m bar u double dot 0 to L xi 1 squared dx plus m bar u theta 0 to L xi 1 xi 2 dx. You see this? This just comes out from there. And so, if I rewrite this, and what was xi 1? Remember, xi 1 was equal to 1 and xi 2 was equal to x. Well, 0 to L by 2 and then 2. So, this basically would become 2 L by 2. Okay. And so, if I do that, what happens? I get the following. F I 1 is equal to m bar. So, I have xi 1 squared is essentially what? I got it equal to xi 1 was equal to m bar L into u x double dot, and then plus, now I have over here 1 into x and 1 into minus x. So, I have both 0 to L. So, I can do it 2 times 0 to L x dx. So, this becomes x squared by 2. So, this basically becomes x dx 0 twice 0 to L by 2 into m bar u theta double dot. So, this is equal to m bar L u x plus, if you look at this, this becomes x squared by 2. So, this becomes essentially 2 into L by 2 squared divided by 2. So, this basically becomes L squared by 4. So, this thing is becomes L squared by 4, okay, x squared upon 2. So, that is the thing, and this into, so it becomes m bar L u theta. Okay. This is my f I 1. Similarly, I can find out f I 2. For f I 2, how do I do? Well, I give it an initial displacement. So, I want to find out, let us go back here. I want to find out f I 2. So, what do I do for finding out f I 2? I give it, which is delta v is equal to xi 2 in del 2 delta u theta, right? That is del v. So, if I go through that procedure and going through the entire thing, what does it become? Well, let us look at it. I get f I 2 is equal to integration 0 to L. I mean, I am just denoting 0 to L as over the length. Okay. It is going to be del u theta. This is going to be equal to f I xi 2 delta u theta. So, if we look at this, f I 2 is equal to, again nominally given in that way, m bar dx xi 1 u x plus m bar dx xi 2 u double dot theta into xi 2. So, that is my f I 2. Okay. So, again what we have is that this becomes equal to the following. It becomes f I 2 is equal to 0 to L m bar xi 1 xi 2 dx into u x double dot plus 0 to L m bar xi 2 squared dx u double dot theta. Okay. So, if I look at this, this essentially becomes the same as m bar xi 1 xi 2. So, this is m bar L squared by 4 into u theta x, and on this one you have 2 times 0 to L by 2. Now, xi squared is x squared dx, and of course, you have m bar into u theta double dot here. Okay. So, what is this? This is equal to 2 times into L by 2 cubed, okay, upon x cubed by 3. Okay. So, this becomes 2 by 3 cubed L by 2. Then, if I have this becomes equal to 2/3 of L cubed by 8. So, this becomes L cubed by 24. Okay. Is that correct? This is L by 2, right. So, 2 by 3. So, 2 into 8, 12. So, this becomes L cubed by 12. So, ultimately, what does my final thing look like? Okay. F I 1 looks like it's equal to f I 1 is equal to m bar L into ux double dot plus m bar L squared by 4. I made a mistake here. It's something that I didn't point out. This one is wrong. We said that this was equal to 2 times 0 to L by 2 xi 1 xi 2. It's not correct. If you look at xi 1 is a constant 1 over the whole length. Okay? And if you look at it, xi is in this fashion. It's plus on this side and it's minus on this side. So, actually it's not twice, it's 0 to L by 2 xi 1 xi 2 plus minus L by 2 to 0 of xi 1 xi 2. If you really look at it, okay, when you go from minus L by 2, so this becomes x, right. So, if you look at it, it becomes, this entire thing essentially becomes x and minus x. That was the mistake I made, that it is really minus L by 2 to 0. So, if I really look at it, this one xi 1, this one is equal to x and this one is equal to minus x. Okay. So, if you really look at it, the whole thing becomes squared, there is no doubt about it. Okay. So, this is minus x squared upon 2. So, when you do this instead of being m bar L upon squared. Okay. So, let me redo the thing, I have done it incorrectly. So, let me just redo this, I am very sorry, I will redo this particular problem. So, let us go back to f I 1. I mean, forget about this, there was this problem where we were doing m bar u theta in the first one in f I 1, which had 0 to L xi 1 xi 2 dx, and in f I 2 we had m bar u 0 to L xi 1 xi 2 dx. So, this was the term that we were looking at, this over L, what is it? Okay. So, if I redo this particular one xi 1 xi 2 dx, this is the one that I am looking at over the whole length. If I look at this, you will see that this is equal to the following. You see, here this is x, right, where x is being taken from here to here and here to here. So, if I take 0 to L, this notional 0 to x xi 1 xi 2 dx becomes the following. The first one going from minus L by 2 to 0, because x goes from here to here, x starts from here. So, this is 0 to L by 2 x dx plus 0 to L by 2 x dx. So, if I look at this, this is equal to, and this is where the problem of trying to double becomes the problem. This is the actual problem. Okay, if you really look at it, this becomes x squared by 2 minus L 0 plus x squared by 2 0 to L by 2. So, if I look at this, this becomes 0 minus this. So, this becomes then L squared upon 8, but minus, because this minus this. So, this becomes minus, and this one over here is L squared upon 8. So, this one is 0. So, actually if you look at it, so that is the reason why in if I rewrite f I 1 and f I 2, what we get are the following. F I 1 is equal to m bar L into u x plus 0 u double dot theta, and f I 2 is m bar L cube by 12 u theta, because again the u x one over here is 0. Okay? So, that is f I 1 plus and f I 2. Okay? So, now let us look at f s. Well, what was f s equal to? The f s, if you really look at it, was equal to. So, now if I were to put in the same way, f s 1 into del u x is equal to integrated over the whole length of what? Of k bar into dx into xi 1 u x plus k bar dx xi 2 into u theta. So, this is the total force, and this infinitesimal into del u, which is equal to xi 1 del u x, because that is del v, right. This is the particular infinitesimal element. Okay. So, again the problem then becomes the following: 0 to L k bar xi 1 squared dx into u x plus 0 to L k bar xi 1 xi 2 dx into u theta. And since we have already derived these, what do I get? This one turns out to be k bar L u x plus 0 into u theta. Okay, that is f s 1. In similar fashion, we will get that f s 2. In similar, I do not want to go through the process. You will get it equal to 0 into x plus k bar L cubed upon 12 into u theta. Now, finally, what do we want to do? We want to put down the what happens to f p. Now, I want to find out f p 1. So, for f p 1, what do I do? I put for f p 1 into del u x is equal to, now I have p bar x, right, that is the intensity at a particular point x dx, that gives me the load, okay, into xi 1 del u x, and this integrated over the whole length. That is what my f p 1. So, f p 1 is equal to, over the whole length, p bar x into xi 1 into dx. Okay. And similarly, we will get f p 2 is equal to 0 p bar xi 2 dx. So, these are our loads, equivalent loads. So, how do I get this for this triangular load? Remember, the load that I had was given in this format, right. It was given in, the load was like this, right. So, if I look at this with my x starting from here, what do I have? This is p bar 0. So, this is p bar 0 by 2. So, what I have over here is p bar x actually is equal to, well, let us look at this. If this is 0, it is equal to p bar 0 1 minus x over L. This is my p bar. Why? Well, let us see. when x equal to 2x by L, x equal to L over 2, P bar x is equal to, well, put x equal to L by 2, 1 minus 1, P bar x is 0. If P bar x is minus L over 2, well, put minus L over 2 over here, you get 1 plus 1, it is equal to P bar 0. So, this indeed is my P bar x. So, now xi 1 is equal to 1 and xi 2 is equal to x. Okay. So, if I do this, what is my f p 1 equal to? My f p 1 is equal to integral, well, I'll do it formally, 0 to this p naught upon 2 into 1 minus 2 x L into 1 into dx plus 0 to L over 2 1 minus 2 x upon L dx. So, if I look at it, what do I get? I get over here, this becomes P naught by 2, that is the first one. So, this becomes x. So, this becomes minus L by 2. So, this becomes L by 2, because 0 minus of minus L by 2. So, this becomes this from this one, and from this one it becomes P naught upon 2 into L by 2. So, that is the first one. Then the next one comes out from here. So, this is the minus 2 x by L. So, if I do minus 2 x by L, when I integrate that, what do I get? Plus, so I will do 2 x by L minus. So, this becomes minus x squared upon L, right, 2 x. So, it becomes x squared. So, the first one is minus to 0 and plus minus x by L 0 to L by 2. So, if I look at this one, what do I get? Well, this one turns out to be 0 minus, so this becomes plus. So, it becomes plus L by 4, this one, and this one becomes L squared. So, this becomes minus L by 4. So, this whole thing becomes 0. So, if I look at f p 1, my f p 1 turns out to be equal to P naught L by 2. Okay. So, that is my f p 1. Okay. What is my f p 2? F p 2 will become nothing but, well, let us put it down now. So, f p 2 is going to be equal to minus L upon 2 to 0 P bar 2 1 minus 2 x into x dx plus 0 to L by 2 1 minus 2 x upon L x dx. So, if you look at this, since these two are identical, what I am really saying is minus L upon 2 to L upon 2 of P naught 2 x minus 2 x squared upon L dx. Well, let's go through this integration, and if you get this integration right, what you get is the following: f p 2 is equal to so this becomes then, so this is my limits, and the inside one becomes P bar upon 2 into x squared upon 2 minus the p bar, p naught bar, 2 and 2 cancelled. So, this becomes x cubed by 3L, okay, and this is the integration. So, if you look at this, since this is minus L and this becomes 0 and this is the only one that is left. So, this goes minus p naught. So, this becomes L by 2, 3 by L, and then plus p naught minus L upon 2 cubed upon 3L. So, if you look at this, this becomes L cubed by 8, okay, and this is again minus L cubed by 8. So, L cubed by 24. So, this becomes then minus p naught L squared, because L cubed cancels, upon this is 8 and 8 24. So, this becomes 12. So, that is my FP2. So, if I rewrite this, so therefore, the equations of motion for this particular one then becomes what? It becomes the following. I will rewrite this now. It comes out as m bar L 0 0 m bar L cubed by 12, okay, u x double dot u theta double dot plus k bar L 0 0 k bar L cubed by 12 u x u theta is equal to, well, what did we get FP1 equal to? FP1 was equal to P naught L over 2, and this is equal to P naught L squared by 12. Okay. So, if you look at this actually, if you look at this, these are uncoupled equations, and what the two equations become are the following. The equations become this: m bar L into u x double dot plus k bar L into u x is equal to P naught L, and the other one becomes m L cubed u theta double dot plus k bar L cubed by 12 u theta is equal to minus P bar L squared by 12. So, you see it is a multi-degree of freedom, but because of the special nature of how I have defined my mass and stiffness, okay, it so happens that this entire equation becomes uncoupled, but it is still 2 degree of freedom system. So, this is how we find out the equations of motion of a multi-degree of freedom system. Of course, I have illustrated this by taking a specific example. Okay? Now, in the next class, I am going to continue with this, and I will show you how we can derive certain important things, and then we will move on to looking at, still going to look at a rigid bar, but after that we are going to move on to flexible bars and see how we can get those kind of equations. Thank you very much. Bye.